So, good morning, everybody. I hope you all had a pleasant weekend and are looking forward to some degree for another fun-filled week in the semester. This week, we are going to be discussing compressible flow and what that means for our mass and energy balance expressions as it relates to fluid flow systems. With today probably talking about compressible flow in general, with a little bit of a deeper dive into isentropic flow, as it's one of the strangest forms of compressible flow that's a little bit tricky to grasp. So I think it's a good idea to kind of discuss it as a group. And, I can answer any questions. And hopefully by the end of this class today, you can have a good idea of what compressible flow means to the expressions that we have so far, mass, mechanical energy balance, Bernoulli's, and how the changes in the fluid properties for vapors and gases influences what we expect to see as it applies to fluid mechanics. So let's go ahead and we'll jump in with our handy dandy notebook. And as soon as I find my pen, we can go ahead and get started with today's lecture. So as I just mentioned, today we are going to be discussing compressible flow. And so up until now, we've largely considered incompressible flow, with the major distinction relating to density. And so with compressible flow, the density of the fluid is strongly dependent on temperature and pressure. And so, when we consider an ideal gas, we have PV equals to nRT. Well, if density is equal to mass over volume, and the number of moles is equal to the mass over the molecular weight, then we can say that the density is equal to pressure times molecular weight over ideal gas constant times temperature. And so for an ideal gas, we see this being our influence of temperature and pressure on our gases / vapors, which tells us that for an ideal gas, density is directly proportional to pressure, and density is inversely proportional to 1 over temperature. So if the pressure increases, our density increases. If our temperature increases, our density decreases. And for a non-ideal gas, we can say that density is equal to PM molecular weight over RT plus some function that accounts for the non-ideality, which we can denote by fugacity and other sort of expressions, if you will. I shouldn't use that. We use that for a different. What do you guys denote for in fugacity in multi-com? I didn't quite catch that.
I don't think we've gotten there in multi-comp.
All right.
I think fugacity was just F, and then the fugacity coefficient was phi.
Yeah, that's what it was.
Phi. Oh, I can't remember how to write phi, so I'm just going to make it F of F just to annoy you. So fugacity and others C multicomp. Which, when we want to get super technical, we, look at our, additional equations of state. Where we can essentially consider the idealized expressions and then the non-idealized correction factors that are a function of fugacity, temperature, pressure, everything else. However, it still boils down to, we can largely consider that the density of a gas or vapor follows this trend where increasing the pressure increases the density and increasing the temperature decreases the density. And so when we consider the implications for this, when we have our wonderful expression for flow through a pipe, if I have my flow coming in, now it's a vapor, so it gets wavy lines. And it's coming in at some pressure here, some density here, leaving at another pressure here with another density. I can say, due to shear stress and other friction sources, the pressure of our fluid will decrease. And since the pressure decreases, I can say for compressible flow, the density of our fluid will also decrease. Right? So density decreases, pressure decreases, following that relation we identified before. And so if I wanted to look at my system, so I make my little system box, because that's how it helps me define my mass balance. And so for my mass balance, I know my mass in equals my mass out, which I can calculate times the density, times my velocity, times my flow area, equals my density, times my velocity, and times my flow area. And so for a constant cross-sectional area, I can state that my density times my velocity is equal to my density times my velocity, right? A1 equals A2. And so that tells me a couple things. One, if my density decreases, or rho 1 is greater than rho 2, then my velocity must increase. U1 less than U2. Also, it tells us that the product of density and velocity must remain constant in incompressible flow. Or excuse me, incompressible flow. And so we can define this product as our mass velocity, which is denoted as capital G, which is simply density times the velocity, which is also equal to the mass flow rate divided by our cross-sectional area. And you can also equate it to a mass flux in our system. If it helps you kind of understand it. And so the units are mass per time per length squared, or kilograms per second per square meter, or pound mass per second per square foot. So it's a mass flux or a mass velocity. And so by our mass balance, if our cross-sectional area remains constant, even though our density and velocity will fluctuate, the product itself cannot. And so the flux of our mass must be constant in our system. Is that clear? Are there any questions, thoughts, and considerations that you'd like to consider, or anything I can clarify or discuss?
Just to confirm, the units there are mass per time length squared.
Yes.
Thank you.
Yeah. So it's basically a mass flow rate per unit area. And so a couple things can arise due to what we see in our system. First, one thing I do like to point out is for compressible fluids, at low velocities, and I'll put quotes around that. We'll talk about what that means here in a little bit. We can consider these systems as incompressible flow. However, at high velocities, these compressible fluids behave very differently. And by behaving differently, I mean they can get complicated. So how do we quantify, quote unquote, how different these things are going to behave? Well, we use a dimensionless number to quantify the relative, quote unquote, velocity of our fluid. And that dimensionless number is our Mach number, which the Mach number is a measure of a fluid's velocity as compared to that fluid's speed of sound at its given temperature and pressure. So I can say U is the fluid velocity, and A is the speed of sound of the fluid given its temperature and pressure. So for reference, the speed of sound, do you guys know what the speed of sound is for air at standard temperature or pressure? I don't expect you to know it, but you know, I don't mind polling the class to see who's speed junkie.
350 meters per second.
That's pretty close. All right, say at STP, it's 343 meters. I'll give you credit for that. That's pretty close. Or 1,125 feet per second, because I know you guys just love English units. For everything else,
Love.
we can calculate the speed of sound as the square root of, I think that's gamma, times the pressure over the density, where gamma is equal to a ratio of the constant pressure heat capacity over the constant volume heat capacity of the gas, which if you just have the CP, you can calculate it like this. I don't know why you would, but it's technically possible. And one thing I will say is gamma is equal to a constant for most problems, and it relates for a specific gas. For example, when we're considering air, because we have a lot of air problems, air and water. I should just call this class air and water, or at least this half. Gamma is 1.4. And so with this in mind, we can calculate our Mach number by combining our expression in terms of U as well as A as the density times velocity squared over gamma times pressure, which also equals the velocity squared times the molecular weight over gamma times T times R. That's just manipulation of the ideal gas equation. And so if you wanted to calculate just the Mach, you just take the square root of everything. But I'll write it here if it'll help you. And keep in mind that the Mach number is dimensionless. So if you do your Mach calculation and you have units, something went wrong. Which, as these expressions have either pressure or the ideal gas constant, so that is a possibility that things can be complicated. All right, so just a quick recap. At this point, after we had talked about the mass flux, I had stated that for compressible fluids, we have to consider the relative velocity. Because at high velocities, aka when you start approaching the speed of sound, things get a little complicated. And so we have to consider what is the velocity of our fluid relative to its speed of sound. And we can calculate this using this expression for Mach number, which is simply the fluid's velocity over its speed of sound, which we can calculate based off its heat capacity, pressure, and density, which combining these two forms, we can get this expression for Mach number. So with this in mind, a lot of times we can consider what happens when our Mach number is 1 and our fluid is traveling at its speed of sound. Or this is when U is equal to A. Well, this is known as a special case, which we have to consider for certain compressible fluids, such that we could denote this the asterisk condition. And so the asterisk condition is simply the properties of a fluid where U is equal to A and Mach is equal to 1. And so a lot of times it's important to know the asterisk condition so that when we design our fluid transfer systems, we don't reach the asterisk condition. And we'll talk about why here in a brief second. And so pressure is P star, temperature is T star, or asterisk, however you want to call it. Density is density, asterisk. And H, when we talk about heat transfer, the enthalpy is H asterisk.
Those P star and T star values, I believe we used T star and P star in 307. Are those the same thing we used then?
That's a really good question. Let me make a note of that, and I'll have to double check because I honestly can't remember in what regard we talked about T asterisk, P asterisk. If I'm completely honest, it may or it may not be. I think when we talked about asterisk conditions there, we were considering the relative ratio of a fluid's properties with that of its critical point when it becomes a supercritical fluid. And in that case, it's different because you can still have a non-supercritical fluid approach a Mach number of 1. And so it's different in that regard. That's a good question. All right. Any further questions? That's a good question and an important thing to consider. Yeah, when you consider vapors and gases, they get a little complicated because of essentially just the non-ideality and how they typically behave. They have so much energy that the properties they exhibit can be difficult to predict and measure. And so what I want to probably talk about for the rest of the day, which we'll see how far we can get through this, is considering a special case. Because when we consider compressible fluids, more often than not, we try to quote unquote lump or control its behavior into one of 3 cases: isentropic flow, isothermal flow, and adiabatic flow. And today we're going to talk about isentropic flow, primarily because it's the most effective way, if not the only way, to obtain what I would call confined sonic and supersonic flow. And this is typically done through the design of what's known as nozzles. They're also called convergent / divergent nozzles or isentropic nozzles. And the design follows something that looks like this. So we have a reservoir of a gas here on this side. Well, let's say it's air. So we got a molecule of air, a bunch of them, right? Lots of them. And we set it up so this zone has a particular pressure known as P. And we set it so that this gas is going to flow into a receiver, which is at a different pressure. Actually, I'll make this one P naught and this one P. Hopefully my expressions don't get too lost in the noise. And so the way it works is we have a converging section. which then follows into a diverging section. And so the fluid flows into the converging section. It reaches a point of minimal cross-sectional area, known as the throat. And then it enters the diverging sections. We have the converging section, the convergent, and the divergent. And so what do you think happens to the pressure in the velocity in our converging section?
They both increase.
You're half right. I'll say one increases, one decreases.
Velocity increases, pressure decreases.
Very good. So the velocity increases and the pressure decreases. And if you want, we might have time for it, we can consider why, right? If we did a mass balance, if I have rho 1, U1, A1, U1, A1, rho 2, U2, A2, I know that my A2 is going to be less than my A1 because in this converging section, the area is getting smaller and smaller. And so my mass velocity, or my G1, is going to have to be greater than G2. Or my G2 is going to have to be greater than G1. Here, I'll just flip this to balance them out. So my mass flux is going to be, quote unquote, increasing because my mass is being forced through a smaller and smaller area. So the pressure and the velocity, or excuse me, the pressure and the decreases and the velocity increases until it reaches the throat. And at the throat, one or two things can happen. The flow can either achieve sonic velocity or fail to achieve sonic velocity. And so at this point, the flow is either sonic or subsonic. And in the convergent nozzle, the flow is always subsonic. And so, therefore, if the flow achieves sonic flow at the throat, then the divergent section can be sonic or supersonic. If it fails to achieve sonic flow, then the diverging section will be subsonic throughout its entirety. And we can consider how and why, which the best way to do this is let's think of what's known as a pressure ratio. P sub R, which is going to be a function of the pressure at the receiver, or P, over the pressure at the reservoir, P naught. So if P sub R is equal to 1, that means the pressure in my reservoir and the pressure in my receiver are the same. correct? So if the pressures are the same at both points, what type of flow should I expect?
Would it be subsonic?
It would be subsonic. I would categorize it as subsonic, yes. But what
Would
can
be no flow.
I could approximate it as no flow. Because if the both pressures are the same, there's no driving force to move the air from my reservoir to my receiver. Now, if I decrease P such that the pressure ratio is suddenly less than 1, then I can expect subsonic flow initially. Which means if I drop my pressure in my receiver, I should start to see flow. But if it's pretty close to my reservoir pressure, that flow is going to be small relatively, and my velocity is going to be low, correct? Now the question then is, what happens when I continue to decrease the pressure in my receiver?
Will the velocity increase?
The velocity will increase with relativeness to the pressures. So when they're equal, there's no flow. As I start dropping the pressure in my receiver, I start to see flow. And as the pressure in the receiver starts to decrease, my velocity and my mass flux and mass flow rate will all start to increase. However, there becomes a limit to this system, in that if I continually decrease my pressure and decrease my pressure ratio, my mass flow rate will reach a maxima, which means as my pressure ratio decreases, my mass flow rate will increase. However, this increase will be limited by the nozzle and the nozzle design. Which means if I were to draw or graph a function, if I could draw, that's the real question, of the pressure ratio as a function of my mass flow rate at a pressure ratio of 1, I expect 0 flow. And so my mass flow rate will be 0. Now, as I start decreasing my mass flow rate, that pressure ratio will start to diverge from 1 to a value less than 1. However, what I'll find is that there becomes a point where I achieve what's known as a maximum flow rate. And any decrease or any further decrease in my reservoir pressure results in no change in my mass flow. So at this point, I have obtained what I call choked flow. And what I mean by choked flow is my mass flow rate, my compressible fluid. I shouldn't say that. That has been limited by confinement / the flow system. I know it's a very generic and vague definition, but it simply means that you've reached the maximum flow rate, and increasing the driving force is going to do nothing for the system. Because any change in the receiver at that point cannot be transmitted to the reservoir. And that's a little hard to kind of consider and understand conceptually. And what I mean by that is, if I have flow, and let's just consider general flow, not even through a nozzle, and I increase the pressure, I increase the driving force, right? That's going to result in more energy in the system, right? Or if I want to push that flow rate, I can continually increase it and increase it with relative ease. However, for a compressible fluid that begins to approach the asterisk condition, the system gets limited essentially by the fluid itself and essentially the speed of sound. Because at that point, the fluid itself cannot relay that information associated with the driving force back to molecules before it. Which means if you try to increase the flow, nothing's going to happen and the system is going to essentially be choked. Here, I'll erase this. That wasn't really helpful.
What did you write before flow system?
Confinement or confinement. By a confined flow system. I will clean this up. That's a good question. However, a nozzle is designed such that for a particular pressure ratio, not only can you achieve sonic flow at the throat, you can achieve supersonic flow in the divergent section of the nozzle. Primarily because when you consider a sonic flow, at the point of essentially you begin to break that sound barrier, you typically have a shock wave, right? A massive fluctuation in energy as that fluid is pushing the air in front of it and behind it. And so you have the accumulation of those molecules. However, these nozzles are designed such that for a particular set of flow conditions, the divergent section allows those molecules to be pushed in a way that achieves a steady flow. And it's only for a very, very narrow set of flow conditions that you can not only obtain the sonic flow as well as obtain stable supersonic flow within the divergence section. And this is best exemplified in figure 6.2 in the text off page 140, where the way it's set up and designed, it's showing essentially a function of the pressure ratio as in terms of the length of the nozzle. And so you have the throat here. Anything before the throat's the converging section. Anything beyond the throat is the diverging section. And so at pressure ratio equal to 1, you don't have any flow. But as you begin to look at and consider the flow or the pressure in the nozzle or the receiver versus the reservoir, you can start to obtain closer and closer to sonic flow. So if you lower the pressure a little bit, the profile looks like this. And then at a certain point, you can obtain essentially P star over P naught at the throat, where you achieve sonic flow, where you essentially design the system that the fluid achieves its asterisk condition at the throat, and that's how you obtain that sonic flow. But in that diverging section, the velocity will start to decrease, and you get into subsonic flow. However, like I said, if you set it such that the receiver is just at the right pressure, you can obtain supersonic flow. And so this is the curve that the fluid wants to follow when you set it up for sonic and supersonic flow. If the receiver pressure is somewhere between the essential point of sonic at the throat and supersonic flow in the divergent section, an issue happens. I think it's denoted here by point J. The fluid will initially follow this supersonic line. However, as the information gets transmitted such that this is the receiver pressure, you essentially have a shock wave hit within your divergent section, which forces the fluid from a supersonic fluid back into a subsonic fluid. This is the shock wave. And so nozzles are designed such that when you set the system to operate between points A, D, and F, you can obtain stable supersonic flow. And it's, like I said, primarily a result of the fact that you have confined flow that you're trying to achieve some form of sonic velocity. And without the proper design of this diverging section, such that the shock wave can propagate in a way that it actually doesn't form a massive fluctuation and loss of energy, you can have that stable supersonic flow. But if I have flow through a pipe of compressible flow, right? Going back to our regular flow through a pipe. If I have some U here, and then in the middle I have some U star, I'm never going to achieve sonic, supersonic flow. What will end up happening is you will most likely end up in choked flow. And so you'll end up at a maximum mass flow rate, which is limited by the design of your flow system as well as the properties of your fluid. So the question I can ask you and is, how do we avoid choked flow? You guys have any ideas? Any thoughts? Oh no. And how we can avoid choked flow?
You probably need a
Self
big enough
system.
diameter for whatever like flow rate and fluid properties you have.
So you can ensure sufficient cross-sectional area for flow. That is one way. Very good. Any other ideas?
Keep your pressure ratio high enough so that choked flow doesn't occur.
All right. I would also characterize this as repressurize your fluid, right? Because if your pressure of your fluid falls, the velocity is going to increase. So one way to decrease the velocity away from the sonic velocity is to repressurize it again. If you add more pressure, you increase the density of the fluid, the velocity will go back down, and you can keep on flowing without worrying about choke flow. You can also minimize your pressure drop. That looks ugly. Yeah, so ensure you don't have overabundance of frictional dissipation, things like fouling. So I'd say ensure there's no fouling or buildup in your system. So there's just some ways that we can avoid choke flow. All right, I think that's a good stopping point. On Wednesday, we'll work an example or two, as well as talk about isothermal and adiabatic compressible flow. Any last minute questions? All right, if not, thank you always for attending. And as always, if you have questions, feel free to send me an email or stop by office hours. I will have office hours this morning. However, there will be no office hours this afternoon as I have a meeting scheduled at 1. So I do apologize for that. If not, take care, guys, and have a great day.
Thank you.
Thank you.
Thank you.